And recording. So this is the ELE 2022 exam. It covers pretty much everything, right? So the question 1 is RC and RL in DC. So that's working with capacitors and inductors in DC. Question 2 is nodal analysis. Question 3 is mesh analysis. Question 4 is Thevenin equivalent, and question 5 is power. As far as I'm aware, I have all of the solutions, and I'm nearly certainly confident in all of them, except, am I not 1080p? I don't think I can stream in, let me see. Stream quality, 1080p, oh. No, it's doing, I don't have Discord Nitro. Here, I'll put it in 15 FPS so it'll at least appear more higher quality. It's because Discord, you have to pay for Nitro, because that's how I'm streaming it. What was I saying? Right, yes, I'm nearly certain on all of the answers that I'm going to provide because, and this is a very nice tip, you have multisim at your disposal. So, to be honest, you can just check most of your answers using multisim, and I'll be showing you the multisim answers afterwards. Oh, I do have Vencord. Let me see if that one works out. Because I wasn't aware that Vencord allowed you to do 1080p even if you don't have Nitro. Let me try joining on that one. Oh, can you hear me? Okay, screen 1,
Yes.
1080p, 15. Alright, that work? Yo, fire. Don't be roasting people's microphones in chat. Alright. So, those are my suggestions just from the get-go before even doing it. While you're studying, use Multisim and MATLAB actually to verify your answers. Because MATLAB has built-in complex number support. It's, you can just put in complex numbers however you want, like 5 plus 2i, and it'll handle it for you. So use MATLAB. Or if you don't have MATLAB installed, use GNU Octave, because that's free. But point is, use those two to solve things. Now let's actually do the questions. What's your PayPal? I'm not giving you my PayPal. I don't trust you with my PayPal. Okay. So, question 1. The switch in figure 1 has been open for a long time. At t is equal 0, the switch is closed. Calculate IL at time 0 and IL at time infinity. So this 0 plus is basically just asking for the limit as it goes to 0 from the positive end, because you can't actually do 0. You get like a divide by 0, I'm pretty sure. So what this is asking is, oh no, the limit just doesn't exist from the, if you take both sides. Point is, what's just asking is, what is the current just after you flip the switch? And what is the current after it's been flipped on for pretty much infinity, as the limit goes to infinity? And also asks us to only use source transformation when solving for IL infinity. So, the first thing we want to do, let's rewrite this. Let's take this down here. So what happens when time is equal to 0? Well, actually, the first thing that... Oh, wait. Okay, so when time is equal to 0... Oh, wait. What the hell? Has been open for a long time. Okay. When time is equal to 0, this circuit is just closed. So what happens? Oh my lord, I'm brain farting. I'm so sorry right now. Okay, let's start with I infinity, because that one I know how to do for sure. So how do we get to high infinity? Well, let's rebuild this circuit with the circuit closed. So we have our first resistor here, 5 ohms. Our second resistor here, 15 ohms. Our current here, current source there, 2 amps. Our voltage source here, 10 volts. Our first resistor here, 30 ohms. And our inductor here at 2 millihenries. And of course, we'll put the ground on the bottom. So let's so as the question asks, we need to do source transformation. And so if you remember, source transformation literally just follows V is equal to IR. The rule is that if you have some current source in parallel with a with some load here, that turns into a voltage source with that load in series, and vice versa. So if you look here, we do have exactly this. We have a current source in parallel with a load here, 30 ohms into millihenries, and we can turn that into a voltage source. Question, yes? Why would you not turn the 5 and 15 into parallel? They're in series. You're asking why don't we combine them? No, like source transformation. You can do that, but generally speaking, parallel lines are going to make your life worse, right? If you have a single circuit like this, it makes your life a lot easier. You don't need to worry about branches. You don't need to worry about all that. That is a very good question. I should have covered that. But yes, generally speaking, when you use source transformation, you want to be turning current sources into voltage sources because you get rid of the parallelism and you worry about less branches. And you'll see how much easier that becomes when we do this. So, actually, let's leave that up. So using V is equal to IR, the current is 2 amps, and the resistance is 30 ohms. Right? Because at this point, the inductor has been going on forever. It becomes a short circuit. I probably should have covered that. This inductor, as it goes on towards infinity, becomes a short circuit. Short circuit. Because that's a rule, right? Capacitors become an open circuit. Inductors become a short circuit when they're completely full. So the voltage here is 60 volts. So let's go and transform this this circuit. Let's take this, copy it, take it down here. So now it becomes in series. And the rule is that the positive end is in the same direction as the current was. And the load goes after the positive end. So this is how it becomes after we've done our source transformation. So what is the current running through this entire thing? Well, at this point, we can just collect, right? 2 voltage sources in series becomes just 1 voltage source. Actually, we don't need this ground at all because we're not finding voltage at all. So these two just become 1. And you'll notice that these two are opposed to each other, right? So this comes out at 10 volts, and this comes down at negative 60 volts. So these two combine into this singular voltage source at 50 volts. And again, just to repeat myself, just to make sure it's very clear what's happening here. Across here, we gain 10 volts. We lose voltage 1 here, we lose voltage 2 here, we lose voltage 3 here, and then we lose an additional 60 volts here. So we can either combine this to be negative 50 volts, or we can put it here as 50 volts. You get the same answer anyway, but negative voltage is weird, so we don't do that. That being said, if you do have a negative voltage, you just flip it around. Let me show that actually. So if we combine it at this point, we get negative 50 volts, and then we just flip it around. Like that. Anyway, so we have 50 volts here. Let's combine these resistors because they are in series. It's incredibly simple. That's 30 plus 5 plus 15. That's 50 volts. And just like that, we have an incredibly simple circuit. This has an I infinity of 1 amp. The inductor is still there, but it's still like a short circuit, right? So we have just determined I infinity using source transformation. And again, source transformation took this circuit, which had a branch, and turned it into an incredibly simple parallel circuit. Sorry, not parallel, series circuit. 50 ohms? Yes, because you have 5 plus 15 plus 30. Is this tutorial beginner friendly? I don't entirely know everyone's sort of like level of knowledge. Oh, I wrote 50 volts. Sorry. You're right. I don't know everyone's knowledge in this, so I'm trying to keep it simple. But if you think like I haven't explained a part, just yeah, okay, I will. But assume everybody skipped class after midterm. If I didn't feel like I explained something, just say it. Because again, I don't know your level. I don't feel like bad that you don't know some parts, because trust me, I don't attend the lectures either. I literally had to teach myself this. So yeah, if you feel like I'm rushing, if you feel like I'm skipping out some parts, tell me. What did I do practice? Textbook, and I did the textbook questions, and I did the final exams. That's it, pretty much. Okay, so we found IL infinity. IL 0. This is the second one we need to find. So as I need to review my notes how I actually answered this, because I may have forgotten. Where did I get IL is equals 0? IL 0 plus is equal to IL 0 minus. Actually, yeah, okay. Oh, yes, you reminded me. Okay, thank you. That's how I did it. So, with inductors, the rule is that, so say if a current is this amount, so this is current over time, it's going to stay at some amount, and then once the change happens, it's either going to drop down to the second level, or it's going to increase to some other level. So, we can find our initial I by looking from the left side. Totally was not asking a question. Yeah, just context. He pointed out something and then I went off it. But yes, he was right. So to find I0, we just see how the current was looking before the situation. Okay, so to elaborate on that point, capacitors and inductors work in opposite ways. So if this is current, right? With inductors, it stays at some level and then it jumps like this. So yes, you can approach it from the left. That's not how capacitors work. Capacitors do this. You can see they jump instantly up and then slowly degrade down. With voltage is the exact opposite. It will stay at some amount, the capacitors will stay at some amount and then drop down gracefully like that. And inductors will stay at some amount and then jump up and come back down. Capacitors and inductors are opposite of each other. They act the complete opposite way of each other. So for I0, we just look at how it was going before the switch was pulled. So let's take this scenario again. This is our circuit here. What the hell? I did not copy it properly. Is there any way you could share the doc so we can go through you? Are you asking about the final PDF? The final PDF is upload. Oh, no? Oh, you mean this sort of like thing that I'm drawing here? Unfortunately, no. This doesn't have the feature. I don't use like I don't use OneNote. I don't even know if OneNote has that feature. So you just have to sort of settle for the stream. So this is a circuit at a negative time, right? So before the switch is pulled. Right now, this is a short circuit, or this is an open circuit. No current passes through here, so this entire left side has no current running through it at all. Completely useless. So let's just cut that out. And we are left with this. So this is time is equal to 0 from the left side. And we have the inductor here, which again has been closed for a very long time. So it is a short circuit once again. And once again, this is incredibly simple to achieve. Actually, it's right there. It's 2 amps. The current at 0 is 2 amps. Because it's a current source. So this entire place has just 2 amps according to a current source. So we now have that I0 is equal to 2 amps. And we have that I infinity is 1 amp. Don't worry, you don't need to force yourself to laugh at my shitty jokes. So there's the first part done. So just as a review, with the infinity part for inductors, we source transformed it to create a simpler circuit, and then we solved the current running through it. With we assume that the inductor is in a short circuit because it's been going for a very long time. At I is equal 0, we leave the we come from the left side, so the circuit is still open. The left side in time. So the circuit is still open, and then we solve for the current. And we get I0 is equal to A, I infinity is equal to 1A. Okay, part 2. Determine an expression for ILT for t bigger than 0. So, this one, we can use the formula. They give it to us. I don't know if they will give this to us on our exam. So I would recommend you know this. So yt is equal to y infinity plus, in brackets, y0 plus minus y infinity e to the negative t over tau. You think they do give that? I'd have to check. They do? It was on 2023 file? Okay, so they probably do give it to you. Side note, I don't like how they use tau. It looks way too similar to time. I got confused on that one. They gave on the past 3 finals. Okay. Do we need to know how to derive this equation? No. This is given, or this is either memorized or given. From what everyone else says, it's given. Yeah.
It's given.
All right. Yeah, it's given. So this is the equation you use for something that has an exponential or a natural change to that. And at this point, we just fill it in, right? So it is equal to the infinity, which is 1, plus 2 minus 1 e to negative t over tau. Tau is in an inductor circuit, it's L over R. And if we do that, so take your calculator and you do, what's that? We had 2 millihenries, so 0.002, or 2 to the 10, 2 times 10 to the negative 3, divided by the resistance in the circuit, which this is after t is equal 0. This is after the circuit is closed, so it's this resistance here. What final is this again? This is a 2022 final. So it's 2 times 10 to the negative 3 over 50. And if you do that, you get 4 times 10 to the negative 5. Just that. 4 times 10 to the negative 5. Don't put units. This is recorded, right? Yes, it is. Let me just double check that it's recording. Yeah, it is recording. Okay, I'm re-recording this segment because I made a quite fatal error early on, and I don't want to bore you with 30 minutes of me trying to solve and figure out why I was being stupid. So, we can, so we formed this formula that's time over 4 times 10 to the negative 5. Now, to make our lives a little bit nicer, we can move this upwards. If you put in your calculator 1 over 4 times 10 to the negative 5, you get 25,000. So let's simplify that out. So that's 1 plus, we can get rid of this because that's just 1, e to the negative 25,000 t. So all we did is move this up by reciprocating it, right? So this is our function, our expression for IL for t greater than 0. The third question here is to determine an expression for VL for t greater than 0. Let's put that down here. So the way that we solve this is that the voltage over time, voltage over the capacitor, inductor over time, is equal to the inductance times the derivative of the current. Like that. Sorry about the coughing. So our inductance, if we scroll up to the top here, is 2 millihenries, or 2 times 10 to the negative 3 henries. So what is the derivative of our function? Well, this is just calculus, right? So VL is a function of time. So the rule is that we do the derivative of the exponent. So that's the derivative of negative 25,000 t times ln of the base, which is just e, so that's 1. That goes away. The 1 goes to 0. E to the power of negative 25,000 t. This derivative just comes out to be negative 25,000. Let's move that ln. VLT is equal to, let's multiply that, 2 times 10 to the negative 3 times negative 25,000. Negative 50 e to the negative 25,000 t. That's it. That's all you do. So next part, draw IL versus time. Let's copy that. Bring that down here. So I don't know if I have drawn this already by the time you're watching this, but this is a graph, or this is the sort of cheat sheet for capacitors and inductors, right? Recall that inductors will, while they're stable, be a short circuit or no voltage difference across. So it's going to start at 0 volts and it's going to jump up and then come back down to 0 volts once it has stabilized. Current is the exact opposite. Current can pass through just fine in an inductor, and the moment that the switch flips, it will come to a slow rest to the place it wants to be, right? Its new steady state. The capacitor operates the exact opposite way. Remember that a capacitor, once it's in its steady state, becomes an open circuit. No voltage. There is a voltage difference, but there's no current difference. So current will do the exact same thing that the inductor does with volts. It will jump up and then it'll rapidly decrease back down to 0. While voltage will stay at its steady state and then it will travel down to its new steady state. So based on this cheat sheet here, right, our current is going to start same time as time equals 0, and it's going to end at some new I is equal infinity. So let's draw this out. We'll do this. T is equal to 0. This is amperage is equal to 2, and this is amperage is equal 1. And this is amperage equals 0. Recall that our I at 0 is 2 amps. So this is our steady state. It goes like this. And then once once it is flipped, it travels to 1 amp. Like this. So that's the inflection point. Let's see this on Desmos. If I go here and I put in e to the t, or e to the x, or e to the negative x, how's that? Plus 1. 1 plus this. And this function really only works for when time is greater than or equal to 0. Before that, it's just going to be like this. X less than 0. So this is our graph, right? It's going to be steady state like this at 2. And then the moment we flip the switch, it's going to travel back down to 1 and stabilize there at the new 1. Let's also see that in multisim, right? Because multisim, again, you can simulate all of the circuits. All of the circuits you want to simulate, go through here, please, because it just makes your life easier. I don't know what to tell you other than that. You know your answer is right, just do it. So, you could take your time to learn this. I'm going to post all of the multisim things in the description or in the Discord or wherever you're checking. So, at time is equal to 0, or before that, it is open. It's open, yes. Let's open that up using A. So, let's start it up. Let's pause that. Zoom out. Like so. So this is how it is. And so how this is set up here is that for every milliamp that goes through this here, it will generate 1 volt to measure. So we expect to see 2 kilovolts. And indeed, if I move this lead around, you'll see I get 2 kilovolts. Meanwhile, we get effectively no voltage. F is, I don't even know what unit F is, but I can tell you it is insanely small. But the moment that we flip this, right? Let's continue simulation. Look at that. It looks instant. That's because the capacity or the inductance is so extreme. Like if I actually put the power here, you can see it looks almost instant. But if I zoom in, there you go. There is a curve. Let's zoom in. Oh, that's perfect. Oh wait, that's the scale. Oopsie. Let me move that scale back up like this. Move it a little bit across. Okay, so you can see here, it starts at 2 kilovolts and then it travels down to 1. Pay attention to this channel B here. That's the amperage. So it goes from 2 amps to 1 amp. Let's look at channel A, or the voltage. You can see after we flip the switch, it rapidly travels down to nearly -50. You're going to be off by a bit because you see it takes some time to get used to, and by then it's already dissipated a bit. You're not going to reach your actual maximum of -50 volts. But it comes back around to steady state to become 0 volts again. So that's an example of the multi-sim simulation. All right, so that was a rocky start. Let's hope that it gets better. Okay, so switch in figure 1B has been closed for a long time. At t is equals 0, the switch is opened. Calculate VC and VC0 and VC infinity. Use superposition principle only when solving for VC 0. Determine expression for VCT for t is bigger than 0, and determine an expression for ICT for time is bigger than 0. Just so I don't repeat myself, my dumbassery, so to speak, does anyone know the equivalent formula for this? I'd imagine it's going to be like some division. Anyway, let's start with the rest. We'll worry about that later. So 1, calculate VC and VC infinity. Let's draw this. Let's draw it out. So we get okay. So it's the same sort of idea. Okay, thank you, Fire. So we get this 12 ohms. This is 18 ohms here. We have the capacitor here. We have another resistor here. This bottom connects up just fine. And then up on the top here, we have a voltage source, 80 volts, connected to a switch, which opens at time is equal to 0. And then 20 ohm here, down. Let's move that down a bit so I can see a bit better. So let's find VC at time is equal to 0. So we have to use superposition for this. And so that means that let's take this, bring it down here. Let's start with the voltage, this voltage first. So let's remove this current source. You replace it with an open circuit. And so we are finding it after it's been stabilized. So this this capacitor here becomes an open circuit. Remember, when it's reached sort of its stable area, capacitors will become open circuits. Inductors will become closed circuits. And so we can remove this entire part here because that's just an incomplete circuit. And remember, there's no current running through here. And what happens to voltage as it crosses a resistor with no current? There's no voltage drop. So we can actually just take this and remove this 18 ohm resistor entirely. And it is asking, let's see, plus here, minus here, VC. Everyone understands why that resistor was removed, right? Because no current running through a resistor, no voltage drop, might as well not exist. And once again, we are approaching from the positive side. So the switch is already closed here, right? Remember the graph? Capacitor, we're looking at voltage, so we're just going to be we're going to be approaching from the left side, the negative side, because this is a lot simpler. It's just flat. I'm confused why you removed the resistor. Okay, so if I have a circuit here with a resistor in here, if there is no current running through it, then the voltage here is equal to the voltage over here. So there's absolutely no voltage drop, so it might as well not exist. That's just a rule with resistors at 0 ohms. There's no voltage drop across it. Sorry, a resistor with 0 current. There's no voltage drop across it. How do we know there's no current? Because it's an open circuit. Because capacitors become open circuits, right? So there's no way for the current to get across. Yeah. So there's still a voltage difference between these two terminals, but there's no current crossing it. And the question is, what is that voltage drop using voltage difference using superposition? So we can also just expand this out even further. We can find the voltage at this point and the voltage at this point. Like this. We can't combine these two resistors because that would get rid of this node. So we can't get rid of that. We can only combine these two because we don't care if we get rid of this node. We're not looking at it. So let's combine the two. And you're going to get a really simple circuit here. 80 volts, 20 ohms, another 20 ohms, and then the voltage difference between these two places. We know how to solve this. This one's easy. You can just use really simple nodal analysis. So the current across the entire thing is a voltage divided by the total resistance. The current's going to be 80 volts divided by 40 ohms, 2 amps. And so you can, so V is equal IR. The drop here is V is equal IR, which is 2 times 20. That's 40. So the voltage here is 40 volts. Because this is 2 times 20. Oop. 40 volts. And this here is 80. And we could just make this opposite side our ground. We kind of just already did that. So this is 0 ohm, this is 0 volts. This is 0 volts. So now we do the positive terminal minus the negative terminal. That's 40 volts minus 0 volts is equal to 40 volts. So that is our V1 or our VC1. Now we need to do the current source. Where are we getting 40 volts from? We start with 80 volts. So we start here with 0. This is our ground. We come across the voltage source to 80 volts. And then using V is equal IR, we could determine that the current is 2 amps, right? The total resistance divided by total voltage divided by total resistance. That's 2 amps. And using that, we can find the voltage drop across this resistor, which is 20 ohms, and thus 40 volts. 2 amps times 20 ohms. That's it. So, 40 volts, that difference. Now we have to do the current source. I did not write the current source here. 6 amps. Okay. And so this becomes a open circuit. Or this becomes a short circuit, right? Because voltage sources become closed circuits in superposition. Once again, this capacitor becomes empty. And the same thing happens here. So now we're just measuring this voltage across here. And we have a current source in parallel with a resistor. And remember, parallels make our lives harder. Get rid of parallels. And how do we get rid of parallels in this situation? Source transformation. So that is that the voltage is equal to I times R is equal to 6 times 12. 6 times 12 is 72. So this is a positive end, this is a negative end. Remember, the positive end points the same way as the current source is going. So up. This is 12 ohms. And we can simplify this entire part to be, so this is the negative terminus. This is a 20 ohms. This is a positive terminus. Or terminal. Same thing. And then we have another 8 ohms down here. And it's asking us what is the voltage drop, voltage difference across this. And again, we do the same thing. We can just do nodal analysis, 72 volts. So we're going to define this point as our ground, 0 volts. All right, coming across, we have 72 volts here. And now we come across this resistor. Let's find I. I total is equal to voltage total divided by resistance total. That's 72 divided by 12 plus 20 plus 8. And if you put that in your calculator, you get 72 over 12 plus 20 plus 8. You get 1.8. 1.8 times 12. This here is going to be 21.6 volts. A little bit weird, but don't worry. And once again, we jump across here. This is getting cramped. Let me move this. 12 times 1.8 drop. And then we jump over here again to find the voltage at this point. This is going to be a drop. So it's 21. This is going to be a drop of 1.8 times 20. 36 volt drop. Is that right? Huh? Oh, I'm sorry. We are, oh wait. What the hell am I doing? Oh, sorry. This is the drop. The drop is 21.6. So 12 times 1.8. Yeah, you're right. I don't know how I made that silly mistake. Sorry. So 72 minus 21.6. That's 50.4. This is 50.4 ohms. Or volts. Let's jump across. This is negative 20 times 1.8 is equal to 36. Actually, yeah, we didn't even need to calculate this. We know that at the, but I'm just going to do it anyway to show a point. So this is 50.4 minus 36 is 14.4. So VC is not equal to 36. This is wrong. Because, again, we're working in not passive mode. VC is 14.4 minus 50.4. They are in series, but the issue is that if we combine them, we lose these nodes. And if we lose these nodes, we can't check the voltage at them. So you see the same sort of thing happened here. The checking the nodes at that point sort of locks that nodes into existing. You can't get rid of them. So you can't combine voltages across nodes that you're checking. So this is actually negative 36 volts. Let me just put that there. There you go. So our second voltage here is negative 36. So now voltage total is voltage C1, or voltage C total, is equal voltage C1 plus voltage C2. That is, what's that, 40 minus 36. 4 whopping volts. So this is, just to remind you again, we are doing this at time is equal 0. So this is the, we're checking from negative side actually. Can you explain real quick the voltage dropping shit? Yeah, so like which numbers correspond to what? So this 72 is this thing here. Let me just highlight that for you so that it's clear which is drop. So this is the drop. I'm going to highlight in green the drop. So this is 0 volts. It starts from 0 volts. It gains 72 volts across this here, across the voltage source. And then it drops 21 volts over this resistor. Again, this is our current. So our current times our resistance. It drops down to 50.4. And then we drop it again by 36 volts to 14.4. However, if you look at the nodes on this, we're dropping from the negative side, the positive side, which is supposed to be higher, is lower than the negative side, which is supposed to be lower. So whenever we do this, we do that the difference in voltage is equal to the voltage on the positive end minus the voltage on the negative end. And so if you do that, the positive end is 14.4. The negative end is 50.4. That's negative 36. This is not passive mode. I forgot what the name is. I wrote it down. But yeah, you need to keep in mind these terminal signs because you can and will get messed up on those. Non-passive convention. You basically just flip the sign. That's it. So another question. What's V1 and V2 again? V2 is the one that we just solved here. So that's negative 36 volts. And VC1 is solved here. This is with the just the voltage source. It's VC1 and VC2 because we're doing superposition. So we solved with the voltage first, and then we solve with the current second. And so you get VC1 and VC2. And the superposition rule is that the total VC is, you can just add them together. So you just do one source at a time and you add them. That's it. So the final voltage is 4 volts. So VC at time 0 is equal to 4 volts. Now we need to find voltage infinity. What's that? Well, so this is as, let's grab the circuit once again. So as time goes on for infinity, this gate is going to be open. Like this. So this entire thing is an incomplete circuit. because the gate opens at time is equal 0, this entire part here became an open circuit. And so we can actually, can you go back up for a second real quick? Yeah, sure, what's up? Let me move this to another page, actually. I just need to copy. Okay. Do you want to copy this part? Here, I'll take a picture. Just a VC? Yeah. There you go. So this is as time goes to infinity. So this source becomes completely useless to us, and we are just left with this. Will this doc be posted? It will. Same with the recording. The capacitor, once again, because it's been sitting there for a long time, is become an open circuit. And we can, again, we don't like branches, and we can just do source transformation once again. So this is plus minus, this is 72 volts. We bring the 12 ohm resistor up here. Where will you post it in Discord server? Yes, and the video. So it's going to be YouTube video. I'm going to post it in the description and in this server. You will be able to find it. If you don't, at me. So this is the positive end. This is the negative end. And it's asking, what is this resistance? Or what is this voltage difference? Well, we could combine the resistors, right? Actually, we don't need to at all. Because remember, there's no current running through this. Current is 0. And when current is 0, just as I said before, the resistance, or the resistors, become 0. So this entire thing is actually just, here's the source, 72 volts. Here's a capacitor. There you go. What's VC? It's negative 72 volts. Because again, we're working with non-passive convention here. So it's going to be negative. That's it. There you go. That's VC as time goes on to infinity. So, there you go. Very nice. So we have found VC0 and VC infinity. Determining expression for VCT. The same thing. There you go. Same formula. And now we don't screw this up, hopefully. So that's going to be VC T is equal to VC of infinity plus. Okay, also screenshot. Yeah, sure. Again, all of this will be posted in like a massive PDF afterwards, so don't worry too much about it. So this is going to be VC infinity plus VC at 0 minus VC at infinity, close bracket, e to the negative t over tau. What's tau? Tau is, that's RC. That's going to be the total resistance across the entire circuit, which is as the switch is opened, right? So this here. The total resistance is 12 plus 18 plus 8 times the capacitance. I don't think I wrote down the capacitance. It's 100 millifarads. So that's microfarads. So it's 100 times 10 to the negative 6. Let's write that down. So that's 12 plus 18 plus 8 times 100 times 10 to the negative 6 farads. This is ohms. And then you get, what's that? 3.8 times 10 to the negative 3. So, now we just fill it in, right? So VC 0 is equal 4, and VC infinity is equal negative 72. So VC, as time goes on, is going to be infinity negative 72 plus 4 plus 72 e to the negative t over tau, 3.8 times 10 to the negative 3. And we're going to be smart again. We can simplify this. We can move it to the top. You do. You actually put it in your calculator. So this is because if you don't do that, you get it wrong. So that 1 over tau is equal to 263.16. You know, I don't like that, so I'm not going to do it anyway. I said all that just to not write it. So, we combine these two terms. (76 e to negative t over 3.8 times 10 to the negative 3. And there's your answer. There's VCT. Dinner break at 8? Sure, we can do that. We'll go for like 20 minutes or something. Again, all of this is going to be posted. I'm going to post a PDF right after. The video will take a while because I have to cut out the first part where I was FNAFling. And, but the PDF will be posted immediately. So, so we found VCT for time bigger than 0. So now we need to find current t, current as a function of time. All right, I'll screenshot it for you. So, current as a function of time is equal to capacitance times the derivative of voltage as a function of time divided by the derivative of time. Or sorry, divided by time. Or it's just the derivative of voltage over time. Again, this is the exact same thing as our inductor. We just flip around the voltage and current. So we do that IC T is equal to the capacitance, which is 100 times 10 to the negative 6. You always work in SI units. Times the derivative. With the derivative, that goes to 0. That comes down. So you get 1 over negative 3.8 times 10 to the negative 3. 76 e to negative t 3.8 times 10 to the negative 3. Again, this is just calculus. Multiply those two, so that's 100 times 10 to the negative 6 over negative 3.8 times 10 to the negative 3. And you get negative 0.026. Oh wait, multiplied by this 76, because this is all multiplied by each other. Sorry about the coughing. Negative 2 e to the negative t over 3.8 times 10 to the negative 3. There you go. You just follow the formula. Verified with multisim as, yeah, verified with multisim. I know that because I did verify, but I can show you it. Let's go open this up. Open up. Oh, let me just close this. No. Close. Open. 2022 1B. If we, oop, there you go. If we run this, where is, there it is. And we close it. Oh wait, no, this is wrong. Oopsies. So this is how it is right now, and if we open it, there you go. So we jump from 4 volts here down to negative 72, which is good enough. That's not good enough. That is the correct answer as far as I'm aware. 72. And the current here starts at 2. It's hard to see, but this is 2 kilovolts, or measuring it's 2 amps, and it jumps back down to 0. So again, you can see the graphs once again that I was talking about. The voltage stays constant and then drops down to another value. The current jumps up and then comes back down to 0. If you're having trouble remembering this graph, just remember, right? Open circuit carries no current, therefore the current is 0. Short circuits can have no voltage difference, so therefore the voltage will be 0. And that's question 1 down. It's been an hour 30.